syndrome and new indication in psychiatry disorder surgery. Thank you.
Thank you very much for the invitation. I have no conflicts of interest related to these studies and presentations. Tourette syndrome is a neuropsychiatric disorder characterized by fond and motor tics, and it presents a prevalence that varies from 0.1% to 1% depending on the age group. This disorder presents also a very high infectability rate in one-third of the patients, reflecting suggests conservative management. The first surgery for this disorder was performed by Baker in Canada in 1962. Since then, many other surgeries were reported, and in 2004, I reviewed the literature, was able to find 80 patients submit to a Baker surgery for the treatment of Tourette syndrome. Many targets were used, both motor and or lymph targets, and the results were not really bad. 49% obtained a good relief of the tics, but at the cost of a very high neurological morbidity, which was of 28%. So we are glad that in 1999, Luis Wunderbar started a new area for fluorescent treatment with the introduction of DPS. Since 1999, many targets have been proposed, and the most used targets in the world are the medial thalamus and the globus pallidus internus, with both its parts, both the motor and the territories. And we proposed in 2004 also the globus pallidus externus. So the usual medial thalamic target is the one proposed by Hazard and Dickman in the early 70s, which includes the ventral vagus internus nucleus, the ventricular gray, and the central medial nucleus. And this target was the one used by Luis Wunderbar, who diffused this target all over the world. Cerebral targets is very close to that, just 2 millimeters posterior. And other authors have also proposed variations of this target, using only the central medial nucleus or the complex of central medial with the parafascicularis nucleus. When operating on the medial thalamus, it's usually done under general or local anesthesia, and intraoperative stimulation usually produces both effects. Less commonly, it can induce a feeling of pleasure or loving, and very rarely it can induce intense fear, somnolence, or agitation, where the target is a little bit more larger than expected. And these are the parameters of stimulation used by these authors. Regarding electron recording, the only finding the technique listing is the one by Cervello and his group, who described it by or three-phased irregular discharge of 20 to 40 Hz. So the second target is the GPI, its motor part. And the coordinates are exactly the same as the ones used for both Parkinson's disease and dystonia. Again, surgery is performed with the patient usually awake, and intraoperative stimulation usually has no effects at all, including on tics. The microelectrode recording is just used to define the medial and inferior borders of the nucleus, and these are the stimulation parameters which are very close to those of the medial thalamus. Finally, in regard to the GPI. This target was first described and used by Roberto et al. In 2005, and it's exactly the target was obtained by direct visualization of the medial and anterior region of the globus pallidus internus, which is exactly where its most anterior medial part projects in the direction of the genius of the internal capsule. These are variations of the same target from different authors. And again, in this case, the patients are usually operated on under general anesthesia, and intraoperative simulation is usually also not performed. And microelectrode recording is just used to determine the inferior border of GPI. And once more, the simulation parameters are very close to the always used for the motor part of GPI and that for the hypothalamus. I don't have any experience with any of these targets that I have just talked about. In the only target I have some expertise is the globus pallidus externus, and that's the one we are going to talk about now. As everybody here knows, the indirect circuit of the basal ganglia has a filter role, blocking unwanted water or behavior impulse to go unblocked through the basal ganglia circuit. So the first step to activate this circuit is exactly the inhibition of the globus pallidus externus by the striatum. But review all the literature available in that era was 1997 regarding all neurochemical, biochemical, animal studies, functional imaging studies, and so on. We were able to find a number of changes in the neurotransmitter environment in the basal ganglia. For example, we were able to define that, for example, there was a B2 dopaminergic hyperactivity, also serotonergic hypoactivity, and also a diuretic hypoactivity. And when we put all that together in the circuits of the basal ganglia, you can easily see that the striatum will over-inhibit the globus pallidus, will not be able to inhibit the globus pallidus externus, which will become hyperactive. And in this situation, the filter role of the indirect circuit of the basal ganglia would be lost. Now you see that also there is a hyperactivity of widespread motor areas like Broca's primary motor area and the prefrontal area. So if you take the basal ganglia circuit open and there is a hyperactivity of the prefrontal area, it would manifest itself as obsession. If the primary motor area is hyperactive, it would manifest itself as motor tics. And if the Broca's area is hyperactive, it would manifest itself as phonic tics, which is the definition of Tourette syndrome. So, in an attempt to have a proof of principle, we designed an experiment to check if doing globus pallidus externus hyperactivity would be able to develop an animal model of Tourette syndrome. And to do that, we performed striatotomy in these rats to remove the striatal inhibition from the globus pallidus externus. And also, we tried to mimic the neurotransmitter environment seen in Tourette syndrome by giving these animals levodopa, ergotamine, and naloxone, so as to produce hyperactivity of dopaminergic system, able to induce tics, or what we believe were tics in these animals, as you can see here. This is the hyperextension of the neck, which is called the cephalic involuntary movements. Now, the same hyperextension of the neck and the red running around to its tail. The locomotive tail. These trunk jerks, as you can see, none of these movements is part of the normal repertoire of these animals. These masticatory or mandibular involuntary movements. And the same again, as well as these four-part jerks. Well, so being the globus pars externus such a big structure, what would be the best part to target it? So the central part of the globus pars externus receives a number of input from the subthalamic nucleus, motor inputs. So this look like as the best part of the nucleus to target on that occasion. And also, in the same region, there is an intersection of the three main globus pars externus territories: the motor territory, the associative territory, and the limbic territory. So we target the central part of the globus pars externus, as you can see here, and there you can see a percentage direct will place exactly in that region. We published our results in 2004 in neuromodulation, where we presented the results in 13 patients. And 10 of these 13 patients were responsive to surgery, as you can see in this figure. And two-quarters of the patients improved from the obsessive compulsive disorder, from the depression, the anxiety, and the attention deficit hyperactivity disorder. And this is a comparison of the GPE results with the other targets. So our results seem to be a little better than those obtained when you make the deep brain stimulation in the other targets. So just to show one example of one of our patients, this was our first patient who was operated on in 2004. Was an 18 years old patient. And here after surgery, 36 months after. The results are usually postponed for at least 10 days. During the first year, the results vary a lot, and then it tends to stabilize after 1 year. Okay, so I was asked to talk about also other emergent indications in psychiatric disorders. And I don't have any experience with any of them except for my huge experience with surgery for obesity, which is about 2 patients so far. The last one operated around 10 days ago. So, when the first trials in the attempt to treat obesity using the hypothalamus to start, I thought myself that, well, it doesn't look logical because hypothalamus with the hunger center and the satiety centers are related basically to eating, with some physiological stuff, does not have anything to do with obesity. And then, when we check the results of the hypothalamus bias for obesity, that's exactly what we see. Very rare reports of improvement of obesity when the hypothalamus is used as a target. As per the nucleus accumbens, it's another story. It's well known that hypofunction of dopamine in the nucleus accumbens is associated with obesity and compulsive consumption of palatable foods, as suggested by many authors. PET studies show reduced D2 receptor availability in severe obesity. And also very interesting is the fact that functional MRI demonstrates increased ventral striatal activation in response to hypercaloric food. The nucleus accumbens is involved in other compulsion-related disorders such as OCD and drug addiction. And in animal models, the nucleus accumbens BS reduce intake of hypercaloric foods and binge-like eating, as first demonstrated by Halper's group in 2013. And also demonstrated by Casey Hausberg group, the connections between the ventromedial prefrontal cortex and the nucleus accumbens shell is perturbed in obesity, and modulating these circuit interactions within the nucleus accumbens shell would ameliorate the disinhibited eating. So that's why I think that that's the rationale for using the nucleus accumbens in an attempt to treat obesity. So based on that, we started a clinical trial, a double-blind crossover clinical trial actually, which was approved in 2018, and we just started this year because we didn't have funding to promote the research. The idea was to operate on 5 patients, all them male with age between 30 and 50 years, with severe obesity, refractory to the best conservative management, and after acquiescence from the psychiatry and psychology teams. So, the exclusion criteria were previous bariatric surgery, prior intracranial neurosurgery or structural brain abnormalities, prohibited surgical risk, obesity secondary to other endocrine conditions like hypothyroidism, pituitary adenomas, and Cushing syndrome, the use of appetite-enhancing medications that could not be discontinued, and unrealistic expectations. We also wanted to know if modifying the environment of the nucleus accumbens shell, if we would change anything regarding the neurotransmitters or some hormones related to obesity. So we are dosaging all these substances that you can see here, and we are doing also ultrasound of the abdomen to see liver steatosis and PET-CT to evaluate the food, the eating behavior, because eating binge or food addiction. We are using 7 scales to try to find that. We don't know which of them will work. We will find later on the project. And we would like to exclude things like the presence of depression or anxiety. And we would also like to know the impact of surgery on quality of life and global functioning. These patients were to be evaluated by a multidisciplinary team involving endocrinology, nutrition, physical therapy, psychology, psychiatry, neuropsychology, and functional neurosurgery. The endpoints of this research the assessment of eating compulsion and behavior and food addiction, the anthropometric evaluation, the assessment of neurotransmitters and hormones, as I told you before, and the evaluation of cerebral metabolism with the PET-CT. Then the provocation with the patients with the DBS on and the DBS off. So this is the study design. The preoperative evaluation, of course, then surgery, then a mini open trial, and which will lead the patient. So since the electrode has 4 contacts, it will be 2 weeks for each contact, both with high frequency and then with low frequency, to check which contact was best and if with high or low frequency stimulation. So it takes 4 months to do that. At the end of each of these mini trials are those scales that I showed you to about feeding and eating behavior would be used to assess these patients. After that, we would have the patients with 2 weeks of stimulation for a washout and start the randomized controlled blind crossover trial itself. We have designed the study such as we do just left side electrode on, just right side on, bilateral sides, and bilateral sides off. Each of these trials during 2 months, with 1 week for washout between these mini trials. Then, after that, we will have the open phase trial with the best setting for 4 months with assessment every 2 months, and 12 more months with evaluation semi-annual. The surgical protocol. We use a MRI, 2 Tesla MRI, with all the sequences. The DPI is performed using the same protocol as in the University of Pennsylvania, because his helper is collaborating with us with the integration of the best part of the shell of the opponents to target. And the target is the region of the nucleus accumbens shell that receives projections from the ventromedial prefrontal area, in particular the subgenual cingulate charges. The microelectrode recording is starting 10 millimeters above the target, with and without provocation, by showing the patient's images of his favorite hypercaloric foods. Then mercury stimulation, all that to establish the boundaries of the nucleus, and then the implantation of the electrode and the IPG. So this is the tractography showing the most stimuli coming from the subgenual stimulus in the direction of the nucleus accumbens, which is its shell. Yep, that's enough. And here you can see that's this was burned in this image. This is the shell of the accumbens on the left side. Here is the projection of the trajectory, and the same here on the right side. So the results to finish, patient 1, intraoperative mercury stimulation had no effects at all. The microelectrode recording no response when presented with images of his favorite hypercaloric foods. He just finished the mini open phase trial and started the randomized double-blind crossover study now. During this mini open phase trial, he lost 18 kilos. Patient number 2 was operated on 10 days ago. We'll start mini open phase within 5 days. So this is the patient, just to show you when we present, that's the resting state, then showing the image of his favorite food and they include in the background application. Thank you very much.